you might think that this title, the topic, is something that we all have heard quite a bit about before, the mid-latitude response to the onset of a geomagnetic storm. So what's new about the work that I'm going to present? First, it's a network of 5 Fabry-Perot stations working together as a network to observe the wind in a new approach that had not been tried before. And the consistency of our results lead us to believe that there's a particular interpretation of our result that's been overlooked in previous measurements. So with that as a bit of an introduction, let me move on then. This is the outline, a few comments about the instrumentation. The result, anomalous vertical winds, identification as to why we see vertical winds, and then supporting evidence from the HOPE satellite as an indication of why the interpretation might be correct, and then summary and thought for the future. So it's just a quick run through as to the way the Fabry-Perot works. The instrument is capable of observing the oxygen population distribution as a function of speed. So you see blue shifted atoms or red shifted atoms relative to the Doppler line center of the line shape of the 630 emission that might be emitted by dissociated recombination in the night air globe or by aurora excitation of the O single D state. So the full width of this population distribution is proportional to the square root of its temperature. So it's possible to observe the thermospheric wind and temperature for a region averaged over the altitude interval of 225 to 275 kilometers. The altitude region of the thermosphere night glow layer of the 630 emission. And we used a helium neon frequency stabilized laser as a way of tracking the instrumental drift and taking out the instrument function to get the temperature. So that's a quick run through of how the instrument works. This shows you the distribution of the 5 stations that we're using in our network that we call NATION, North American Thermosphere-Ionosphere Observing Network. So that's one acronym that I know. And so we have 5 stations here distributed more or less in the meridional direction from Ann Arbor, Peach Mountain, and University of Illinois over here, and then Eastern Kentucky University here, just 20 miles from where I grew up in Kentucky. And then Virginia Tech over here on the campus of Virginia Tech. And then the station in North Carolina, which is at the Pisgah Astronomical Research Institute, just a 90-minute drive up into the Blue Ridge Mountains. The circles and squares and triangles that you see here represent the observing direction for off-genus observations, north, south, east, west. But the system is clever enough to go into a common volume mode involving 2 line of sight from 2 different stations intersecting with each other, so they make it possible to observe the zonal and meridional wind component of the wind vector in the same common volume. And considering the cluster of points that we have here, we even have a tristatic common volume, making it possible to get the vertical wind in the same region as the zonal and meridional wind component. Each one of these stations has a cloud sensor, so it's possible to determine if it's cloudy or not automatically. And so the system is designed to respond to that real-time indication of clouds. So if it's cloudy, then they go into cardinal direction. If it's clear for 2 stations, then those 2 stations go into a common volume mode. So it's possible to shift from one strategy to another depending on what happened in regard to cloud cover for the 5 different stations. And the internet connectivity is such that, that the data is sucked out of each of the 5 stations, transferred to the University of Illinois server, analyzed, and the results posted. So I can go into the office each morning, and the results are all done in online available. So it's the state-of-the-art technology that you see represented by this network. All right, so I'm going to talk about the result that we got for the relatively moderate geomagnetic storm 1-2 October. And the station were enjoying clear skies, and it happened that we decided at the time that we wanted to do cardinal direction observation. So we got 5 unit point measurements and 20 off-unit point measurements at the same time over that whole region of the Midwest that I showed you in that map. The storm was not terribly strong. The DST came down to -75 or so. The KP was of the order of 6 or 7, around 5 UT on the 2nd of October. So a baby of a storm, if anything, you would say. Yet the results are very interesting. Here's the plot of the intensity for the 5 stations. So here the normal night glow associated with dissociated recombination, and all of the profiles are normalized together to this period. So this is about 35 to 50 Rayleighs of 630. Then the aurora comes in, and we have major enhancement. Here we have the temperature plot for all 5 stations, and we see a major increase of 400 to 450 K that you see here. So clearly it got quite hot. But the really interesting thing that we saw on this evening was the fact that all 5 stations showed anomalous vertical winds of the order of 200 meters per second downward. And this is very unusual and very much greater than any vertical wind that you would expect as a result of nominal behavior of the atmosphere. So what's going on to generate these very large vertical winds? The big question. We can use the model and the vertical wind measurement to extract out the contamination of the off line of sight measurement to determine the horizontal wind. And the zonal winds then are seen to be fairly modest, -50, 75 westward here, and then eastward here. This is for 2 latitudes, 42 north, that of Ann Arbor, 37 north, that of Virginia Tech. The winds in the meridional direction pick up to 400 meters per second. So this is much larger than the nominal nighttime wind of 150 meters per second that you might see. In spite of the very large vertical winds, we are able to extract out the horizontal wind component free of any contamination. Given that we have now the horizontal wind as a function of latitude, we can determine what the vertical wind might be as a result of the continuity equation. Horizontal continuity equation allow us to calculate the vertical wind. And we see that for the convergence, we have several meters per second vertical wind as a result of the convergence or divergence of the horizontal flow, which is about 2 orders of magnitude smaller than the observed vertical wind. So what's going on to generate the very large vertical wind? It can't be a result of bulk motion, downward motion of the thermosphere. So what could it be? Another clue as to something that is wrong is the anisotropy of the temperature. You see a temperature separation here of 100 to 200 K for a region that's overlapping line of sight. This is a common volume region, pretty much, and depending on the direction, whether you're looking south from Ann Arbor or north from eastern Kentucky, the temperatures are different. Before the storm started, the temperatures are pretty much in agreement. So this indicates something is going on. And that something we believe is the result of fast oxygen atoms precipitating into the thermosphere region. It harkens back to the 70 ideas of neutral atom precipitation. This is a simulation that illustrates the point. Here is the line shape, the thermal line shape that you would expect for dissociative recombination, thermalized to the local neutral temperature. This is the population of fast oxygen atoms that hypothesized to be in place. And the composite is what the Fabry-Perot analysis would analyze to determine Doppler shift. So the fast oxygen atom might have a line center that shifted 900 meters per second relative to the thermal Doppler line center. But the composite would then produce a Doppler shift overall of about 100 meters per second. So this indicates then that the very large anomalous vertical wind downward that we're showing is probably a result of the contamination of our thermalized oxygen population by the population of fast oxygen atoms. And where would the fast oxygen atom be coming from? Well, charge exchange of incoming energetic ions would produce the fast oxygen atom that I indicate here. A momentum transfer mechanism would also apply, and it's possible that fast proton interaction with oxygen might transfer momentum to the oxygen atoms as well. And of course, we're all familiar with the early discovery of the space age relating to the incoming flux of O+ ions, as we saw in the video a couple of days ago. And the latitudinal distribution associated with this work, similar to the vertical winds that we show you in terms of its latitudinal distribution. Interesting enough, this paper by these authors produced a prediction of spectral shift associated with downward oxygen atoms connected with energetic ions coming in. And the prediction of the oxygen, of the spectral shift for the red line of oxygen is indeed consistent with what we observed. So it all sort of worked out very nicely. And then it turns out that the probe observation of energetic O+ ions is consistent with what we saw. Let me show you. This is the field line footprint for probe A, which indicates that the observation that the field lines associated with field lines going into Siberia and Alaska. Here is the observation for the night before the storm. Nothing much is happening. Here is the observation for the period of the storm, and here is the O+ energetic oxygen atom, ion. And if you look at it more closely, comparing with the anomalous vertical wind downward, you see a nice correlation between the injection of low energy O+ ions that you see here between a few eV and a few keV, and the downward vertical wind that we observed with our Fabry-Perot system. So, in summary conclusion, we feel that these observations are very consistent with the identification of anomalous vertical winds with contamination of the thermal profile of oxygen that the Fabry-Perot is observing, and in such a way that the result produces a Doppler shift that is not representative of the flow of the thermalized oxygen atoms. And that would also explain the anisotropy that we showed you, because that would depend on which the direction you look into the thermosphere would influence the location of where that population of fast atoms were relative to the thermalized population. And the fact that we were using a multiple Fabry-Perot network like that of Nation, we feel enhanced our confidence in the conclusion that fast oxygen precipitation was indeed detected in all these observations. A few questions for the future. What are the spatial and flux distribution of the O atom precipitation? Do the properties look like that of a proton diffused aurora? Can the velocity distribution of these incoming fast atoms be measured with a higher resolution Fabry-Perot instrument? I think so. And what effect do the presence of these fast atoms have on the aeronomy of the Magnetosphere-Ionosphere Thermosphere processes and the related reaction rate? And is it possible for ISR systems such as that of Millstone Hill and Ice Cap to observe neutral atom precipitation? I did have a conversation with Joe Dubnik this meeting. He was encouraging that the answer is yes. It would require the increase of the bandwidth for the ion line. And our dream for the future, we would like to expand the network of Fabry-Perot to include all of the North American continent. Thank you.
There we go. That's very interesting. Always good to hear something new that you don't know about before. At least I don't know about this. But at what altitude are these measurements made, and how deep into the atmosphere would you expect these energetic neutrals to be able to get?
Well, the volume emission profile for the red line night glow is of the order of 225 to 275 kilometers. So we're averaging the winds over that region. The high viscosity of that region generally smooths out any variation. So the charge change reaction of the incoming injected ion with the oxygen of the thermosphere would have to take place 300, 350 kilometers, and then there would be a flux of incoming downward moving O atom. I'm not sure if I responded directly to your question.
Well, the first part, yeah, but how far would they go?
The energetic atoms depends on the nature of the collision. That paper, Ishimoto and Ramit and the other did the calculation along those lines. They had a model. They calculated the number of energetic O atom that would be generated at the base on the basis of the flux of incoming energetic ion, and they did this calculation. So it's all the details are all laid out in that paper.
Actually, there is a relatively new paper, John, by Shaba Fang on, I believe, O plus precipitation, high charge exchange, and how it spreads. So you should look at that, Fang. Shaba Fang.
All right, I'll talk to you later and get the author's name. I didn't quite hear.
Yeah, well, I first apologize, and maybe I'll embarrass myself because I wasn't listening as well as I probably should have. But I mean, it seems to me that your Fabry-Perots for this event are located well equatorward of any auroral activity or any precipitating energetic oxygen ions of the Sharp-Shelley-Johnson type. I'm really puzzled. So tell me what I should have been really listening to.
Well, it's a good question. And Greg Earl, one of our co-authors on the paper that's been submitted. And Michael, where are you? It's in his hands. Greg asked that very same question. I can say that aurora was seen over New Hampshire that very morning. And there was a red arc also seen from Boston University sky imaging system. And the data showed very strong increases very significant increases in the red line emission. So there definitely was aurora. It was just relatively weak compared with the visible aurora that we're accustomed to associating with the term aurora.
Not the type of aurora that you would associate with.
Well, it would be diffused. It would be soft soft particle precipitation, more or less.
Can I make one more just really quick comment on that regard? One of the really common features in the Imagina observations, VNAs, was low altitude emission at low latitudes, and it was a very bright feature that was extremely common in that data set. So I would assume these are correlated.
Okay, we're going to go ahead and move on. Thank you very much.